Did I unmute? Okay, good. Thanks. So thanks for sticking around for the final talk on our Yang-Mills afternoon. Indeed, I'll be speaking about the kind of the follow-up talk of what Hao just presented. So I'm going to go into a little bit more detail on a couple of the difficulties that we encountered when carrying out this work. In particular, I'm going to first speak about, I'll go here. So first of all, I'll speak about this identification of the limit that Hao mentioned. So how do we actually know that how to identify what this limiting dynamic is that we took from the lattice? So perhaps logically this should have gone into Hao's talk, but just for time constraint, we decided that I would speak about it. Then I'll speak about this. How do we push this result of this universality for the dynamic to tell you something about its invariant measure? And I'll speak about some of the elements that go into that, and then at the end I'll speak about some of the corollaries about this. So, what can we actually learn about the dynamic as well as about the measure from this kind of connection that we construct? Okay, I'm going to subject you one more time to another diagram of this gauge covariance property. So one more time. So there was this, I'll use Hao's notation for this work. CCHS is this work that we did with AJ, Hao, and Martin. So in 2 and 3 dimensions, if you start this now very familiar Langevin dynamic that we've tortured you with for the last 2 talks, so this is if you consider this Langevin dynamic with this extra de Turck term, and you renormalize in a very special way. So if you choose this renormalization constant in a very particular way, then if you start the dynamic from 2 different points, A and B, then this evolution in the space of 1 forms of these 2 paths will of course be different, and they're not going to be equal in law. But this very special thing, and what makes this kind of choice of C quite special, is that when you project them down to the space of gauge orbits, so 1 forms modulo gauge symmetries, they actually give you the same process in law. Okay, so this is yet another diagram of this result that you saw. And this result in this paper was very much local in time. So we don't know that the process downstairs, for example, in the space of gauge orbits, lives for all time. Okay, so let me also summarize the result that Hao left off from. So on working on now restricting to 2 dimensions, the result that Hao concluded with was that basically for any nice lattice Yang-Mills model, if you consider its Langevin dynamic, which was this collection of SDEs indexed by edges of the lattice, this converges to, in limit, a priori only locally in time, to a continuum PD of this type. Maybe I'll also point out that the Yang-Mills models that we look at on the lattice a priori might impact this C bar. So this is something that one actually has to show that this C bar does not. It's not impacted by the kind of the actual model that you look at. Anyway, so the immediate question, and this is the first thing that I'll talk about, is do we actually know that the C bar is the same gauge covariant constant? So the same canonical kind of more or less canonical solution that we built from in the previous works. So what's the problem with actually showing this? So this constant C bar is indeed it's in principle computable by hand. It's a finite collection of stochastic integrals, but there's really a lot of terms that enter this. So as Hao pointed out, this is given by a huge number of elements that are kind of like finite shifts. They give you a finite shift into this mass. So there's a lot of them. Another difficulty is that we're not. So you might say, okay, well, I want to hit the limit that I know is the good gauge covariant limit in the continuum. So why don't I just renormalize my original? Why don't I insert the correct mass counter term into my discrete Langevin dynamics so that I hit that? So like if they're not equal, I just insert the difference between them into the dynamic. So you can't really do that either because you're not allowed to renormalize this discrete dynamic. This discrete dynamic is somehow just given to you. If you renormalize it, you'll break in its invariance. So you'll break its the fact that it has a nice invariant measure and the fact that it has a good gauge covariant property. Okay, so our strategy instead is to really show that this constant C from this work is actually really unique. So it's really the only constant that you can. So in previous works we had no uniqueness statements about these this kind of property. So now we really show that this constant C that gives you this picture is really unique. So in a sense, this first part is actually independent of this lattice. So this result has nothing to do with the lattice approximations. This is just a result on the continuum dynamic directly. And we wanted to point this out because it's something that really leverages the underlying geometry of the problem. So I think this is an interesting somehow an interesting way that we identify this limit. Okay, so I'll give the result first. So consider any other constants C bar that's not this good constant C. And then you consider two equations started from gauge equivalent initial conditions, and for one of them we're just going to take it to be 0, and the other one is going to be a gauge transform of 0. So very simple initial conditions for these two SPDs. Then the statement, so the thing that allows us to conclude that C is really unique, that gives us this gauge covariant constant, gauge covariance property, is the following result. So there exists a loop, so a continuous smooth map from the circle into the torus, such that for all times sufficiently small, there exists this choice for gauge for G. And I remind you that G enters the initial condition for B. So that's how this connects with the previous statement, such that you can separate these two dynamics via a Wilson loop observable. Wilson loop observable coming from this loop. So, and you can separate it by something which is very precise. So it's something of order t squared. So what is this Wilson loop observable, and why do we care about it? So Wilson loop observables are defined as trace of the holonomy of A along L. This is just a complex number. So Wilson loops are functions from one forms into complex numbers. And this holonomy is defined as, this is essentially a parallel transport. So what are one forms good for? Well, they're good for integrating things along a line. You can integrate one forms along a line, and sort of that gives you a path into the target manifold, target space of the one form, which in this case is a Lie algebra. So we can develop that curve into the Lie group, and this is what we call the holonomy. So you're solving this linear ODE, and at the terminal time y1, you've gone all the way around the loop. And so the very special thing about these Wilson loop observables is that they essentially separate gauge invariant. They essentially separate non-gauge equivalent one forms. So more precisely, if two one forms are equivalent, then all of their Wilson loops agree. So it's just sufficient to demonstrate the existence of one Wilson loop for which these two guys don't agree, and then you can conclude that they weren't gauge equivalent. And so here we have a probabilistic version of that where we separate the expectation of two Wilson loop observables. And then you should compare this result to the case when C bar is actually equal to C. So when we choose the good gauge covariance constant, because then you can show relatively easily that these expectations are bounded from above by any power of t. So in particular, you can take m to be bigger than 2. And the reason that, I said that A and B should be gauge covariant if we take the good constant. So you think that this should be equal to 0. So this t to the m just shows up because we don't know that this SPD survives for all time. But it does have a lifetime whose inverse that has inverse moments of all orders. So this is This is the reason that we put a large power of t here rather than just 0.
So can I ask,
yes.
How does this compare with what Martin was talking about, that C and C, another C converges to a constant? I'm sure I can answer how it compares, but this C here that we put into the dynamic is that constant that Martin was talking about. So this C is the one that Martin alluded to that you can renormalize. So that's the relationship. But here you have only one C, but Martin said that
you can see it in compares to something that's constant.
I think that was in the proof of the fact that you can choose this C to have this property. I actually don't. Yeah, right. Yeah, I don't exactly remember what you said.
Somewhere there's a problem. I think that you have a one parameter candidate and the index by there's no conventional way to put it to zero. You could just choose the zero in such a way that by definition the correct guy you want is the one you see from zero and you just put it right there.
Mhm.
So,
Yeah.
natural things to achieve and that gives you an origin somewhere.
Yeah. Yeah. So like for Martin's talk, basically the takeaway, at least my interpretation is that there existed this constant C for which this thing hold, and that was proved by taking these differences somehow.
Yeah, that's what I get. That's probably
This is right. This is the K. Yeah, this is Martin's K. Yeah. K plus the renal K plus the BPH that constant.
you'll see you don't pick it because diversion.
You're right. Well, but that's because of, I mean, yeah, there's in two, yeah, right. So in two, yeah, maybe I can even say this now. In 2D, this C is finite, so it's a fixed constant. So there's divergences, but they actually cancel each other out. It's very special to two dimensions. Okay, so so basically what we're so I'm gonna give a brief sketch of the how one goes about proving such a result. So there's essentially two cases, and we treat them relatively differently. So these two cases are kind of extremes on how the structure group G might look like. So there's the abelian case, in which case the structure group is like U1, and for which I call this topological because we essentially apply a topological argument, and we really use the fact that we're on a torus. And then on the other extreme, there's the semi-simple case. So when the Lie algebra, or rather semi-simple, then we can actually, we'll see that there's actually more rigidity, and we can say a little bit more. Okay, so in fact, I mean, general compact Lie groups don't fall into these two categories, but via kind of a product and then a projection, you can essentially reduce it down to these two cases. So I'll start with the abelian case, which is the simpler one. So suppose G is equal to U1, in which case the little Lie algebra, the little G, which is the Lie algebra, is just I of R. So I prefer to put I into R. And in this case, it's relatively easy to show that this constant C that you compute is just zero. So in the abelian case, it's just the stochastic heat equation, and you don't need regularity structures or anything to solve it. So this all of these nonlinear terms, which are in terms of Lie brackets, they all just vanish. So it's this is like a two-line computation to show this C is equal to zero. So then, and in this case, kind of this gauge equivalence is given. So if A and B are gauge equivalent, then this is equivalent to saying that there exists a G such that this you can kind of subtracting the gradient of G, you get B. And then we suppose that we take any other constant C bar, which is not zero. We consider two SPDs started from two gauge equivalent initial conditions, zero and this pure gradient of a gauge transform G. And then, I mean, this is just a stochastic heat equation, so you directly know what the relationship between B and A is. So they just differ in their initial conditions, so you can just write this out. So it's the propagator of the linear part of this equation. You put it onto the initial condition. It's a very simple relationship between A and B. So then, so what's the kind of the key remark? The key remark is that while A minus a gradient is always gauge equivalent to A, you can find gauge transformations in physics. They sometimes call them large gauge transformations, such that if you multiply this gradient by a very small number, delta, then this is not going to be gauge equivalent to A. And this is a property of the fact that gauge orbits are disconnected. This is where we use the fact that we're in a torus. So okay, so more precisely, how does one make this remark efficient? So we consider a non-contractible loop that winds around the torus.
We take for this initial condition of B, so remind you that B equation had initial condition, which was the gradient of G. You take it to be something that along this loop it winds around U1. So this is a loop, and I just take G to also wind around the loop. So G is a function from the torus into U1, so it just winds around U1. So G lifts along L to a non-contractible loop in U1, and such a G will have this property. Okay. And then you can write out B1 as being essentially just so this is a repetition from the previous slide, so you know exactly how B1 and A1 are related. So these are the two stochastic heat equations with different initial values. And you see that there's this minus I2 pi, which was my choice for the derivative of G, times this e to the TC. And you don't see the Laplacian because dG is actually constant. So, and you expand this out in powers of t, and you see that for very small t, if C bar is non-zero, then this difference between A1 and B1 is essentially of order t, plus something which is I2 pi. But I2 pi is when you put it inside of an exponential to get the Wilson loop vanish, so it doesn't impact things. So you can so you exhibit this difference between these. So then the Wilson loop of A and the Wilson loop of B is just e to the line integral of A along this line, and minus e to the line integral along B. And you can show that actually in the Wheeling case you get a stronger result, which is that you can bound this from a below by something of order t. This result really relies on the fact that we're in a torus, or more specifically a non-contractible space, so a non-simply connected space, because the result is otherwise just not true. So you don't have uniqueness of the C for an abelian gauge group, for an abelian structure group. So if you're in a simply connected manifold. Okay, so the semi-simple case is harder because the SPD is now nonlinear. So what's the underlying strategy? So we kind of, broadly speaking, we want to replicate the abelian strategy. So we want to look at something which happens at short times. But now we're not in a linear setting anymore. So what we do is we do short time expansions. So I'll come to what these short time expansions are. So by applying gauge transformations, you can essentially reduce the problem of proving this separation of Wilson loop observables and expectation to one that looks very similar, except where we do a gauge transformation of the B equation. So what we do is we gauge transform B to have the same initial condition as A. And when you do this gauge transformation, you pick up a term, and this term is really the difference of the constants from Martin Stock, because if the C bar was equal to the good constant C, this little c would be 0, and for any other constant C bar, this is a non-zero value. So you assume that this linear operator little c is non-zero. So that's equivalent to saying that C bar is not zero. Is not the good constant C. Okay, and then this G equation solves some parabolic PD involving B that we don't really care about, and the whole kind of business comes down to choosing a suitable initial condition for G, so that we can exhibit a difference between these A and B. So trying to think of this B as being gauge equivalent to the B from the previous slides. Okay, so the short time asymptotics here manifest themselves in an Euler estimate for the SPD. So what do we mean by an Euler estimate? So let's take let's call H the initial condition of the derivative of G, which itself actually solves the PD, but it's not so important. Then we can write out the solution B. So B B to this PD as some field psi that's explicit, at least in principle it's explicit, and something that's linear in H and of order t, and something that's of order t almost t squared. So then this So this is something which is linear in H, but in principle it could be quite complicated in H. But the point is that it's independent of the solution B. So if you do the same Euler expansion for A, where H is just 0, so A didn't have a gauge transformation part here, so the H for A is just 0. If you do the same expansion for A, you get exactly the same expansion, but this term vanishes. So then you know exactly what the difference between BT and AT is. So it's something linear in H and something of order almost T squared. So this essentially, so in doing this, we were quite inspired by work of Davy and Rough Paths and follow-up work of Peter Fritz and Nicholas Victoire. So where they do these, they give a solution theory for rough paths, which is in some sense a precursor to regularity structures via Euler estimates. So we were a bit inspired by this work. And so here, the way that you actually do this is you get this result on the level of model distributions for people familiar with the regularity structures in the room. We more specifically, we need to basically feed the equation to itself 4 times, deriving an approximate equation for it. So in some sense, in numerical analysis, this is actually a very standard, a relatively standard procedure, but we needed to do it at the level of the model distributions. So that was one Euler estimate. We have to actually do another Euler estimate, which is for the Wilson loop themselves. Remember, we're interested in Wilson loops of these one forms A. So we now know what the difference between A and B looks like, but we need to apply Wilson loops to those. So Wilson loops are essentially can be written out as iterated integrals of the line integrals of A. So you follow your loop along the torus, and you integrate A, and then you look at all of these iterated integrals, and then you take their trace, and then you pick up a small error, and then you get the Wilson loop observable. So then basically at this level, you also need to do like this is essentially also an Euler estimate for the Wilson loop. So this is a much more standard kind of Euler estimate, and all of these integrals can actually be interpreted in the sense of Young. So so if you our A is roughly the regularity of the Gaussian free field. So when you integrate it along a line, you get something which is alpha wholly continuous for alpha smaller than 1. So you can make sense of all of these. So this gamma is alpha wholly continuous, and you can make sense of it for you can make sense of all of these integrals in the Young sense. So then if you kind of apply this if you now take the previous result and you plug in this expansion into here and you control all the differences in the errors, you can get another expansion which is now for the expectations of Wilson loop observables, and what it tells you is that there's a linear term, which is this is very inexplicit and linear in H, and it has some blow up and has some decay in T, but it's not so important. And then there's this very explicit T squared term, which is just the line integral of H, and you hit this little C on it, and you square the whole thing. And then you take the trace. And so there's no, so I want to point out that there's no order T term in here because we've taken traces, and trace in the semi-simple case, remember we're in the semi-simple case, trace of G is just 0 in the semi-simple case. This is quite important and actually a source of kind of a source of issues, because this is why in the final result we get a T squared rather than a T. So in the abelian case, you had a T because trace didn't kill elements of the Lie algebra. So now the catch is that we have these two, we have this expansion for the difference of Wilson loops, and we want to exhibit an H for which these two guys, they don't cancel, basically. So so this is something of order T squared. This is something of some order that you don't know. It's actually of low order than H, but it's linear in H, and this guy was quadratic in H. So you want to somehow find a gauge transformation that has whose gradient is this H, for which these two guys, they don't cancel. This is the point. So so here you have to leverage the fact that you're in a semi-simple case, and what that means is that actually you can equip products of the structure group G with the Lie algebra. You can equip it with a sub-Riemannian structure. So a very special property of semi-simple Lie algebras is that any element can be represented as a bracket of two other elements. So this kind of, you can see that this is kind of like a Hormandus condition for vector fields. And so basically what you can do is you can find two gauge transformations, G and G tilde, such that they have relationship, so their gradients are like some multiple of each other. Here we took 4, and x. So sorry, x is supposed to be this line integral of h. So c applied to this line integral of h is non-zero. Okay, and the fact that this guy is linear actually gives that one of these choices, g or g tilde, they both can't kind of be 0 in this instance, but just because of, so this guy scales like h, but when you multiply it by 4, it scales by, so you get multiplied by 4, but then this guy gets multiplied by 16. So sort of like, if this guy didn't work, then you can just show that this guy has to work. It's very important that their difference in like a scalar multiple, which is why you need this a special result from subdomain geometry. So this Chandra-Hairer-Shen theorem gives you the existence of these guys. Yeah, so I mentioned that the semi-simple case is a little bit more rigid, and so what that means here is that this argument actually works for non-simply connected manifolds. So this somehow so here we didn't use the fact that we're in a torus, and actually this loop could have been a priori arbitrary, although when writing it up we use the same loop. But this kind of gives an interesting kind of exhibits quite an interesting difference between the behavior of abelian theories and semi-simple theories. So yeah, in conclusion, this argument identifies this limiting constant as the good guy. So this C is really the unique one that gives you this gauge covariance property, and this is how we conclude this universality. Okay, so in my second part, for which I have 20 minutes or so, I'll speak about another one more aspect of this work, which is how we actually show that how do we connect this universality with the invariant measure. So let me state more formally a theorem that Hao alluded to. So in 2 dimensions, this bracket of A is what I denote by the gauge orbit of A. So we can show that this has a unique invariant probability measure, mu, on the space of gauge orbit. So omega here is the space of one forms, and this tilde is gauge equivalence. And moreover, we know that this invariant measure is really the Yang-Mills measure. So which was previously constructed by using exact solvability properties of Yang-Mills. Okay, so on a high level, what are the steps that enter the proof? So we find discrete approximations of this Yang-Mills measure. So we're going to take something called Bourgain approximations. But it doesn't really matter which one we take at the end, such that discrete approximation that converge to the good SPD. So we just finished this argument, and then the second part of the proof of this theorem is that we need to derive moment bounds for this measure. And these two steps, they combine into something which is called Bourgain's invariant measure argument. So this was introduced by Bourgain in the 90s, and I'll just briefly explain how this works. So you can describe it essentially this is a complete proof on one slide, or a complete description of Bourgain's argument on one slide. So kind of, you know that these dynamics, so by A epsilon I mean the dynamic on a lattice with spacing epsilon. It suffices, so you know that these guys converge locally in time to some stochastic PD. So it suffices to show that uniformly in epsilon they don't explode. So that's kind of I think quite relatively believable, because if they exploded, the only way that they couldn't converge globally in time is if they exploded. So we actually took this argument from a paper of Martin with Konstantin Matetsky, at least where we learned about this argument. So the basic idea is as follows: you want to bound the probability that the supremum of your discrete dynamic is large over an interval, a fixed interval of size 1. So what you do is you chop up this interval 1 into k pieces. So each piece is of length 1 over k. And you use the fact that your dynamic is invariant to sort of say that okay, so if it crosses some large threshold L, must have crossed the threshold L on one of these pieces, and so you can just upper bound that by some of the probabilities over these individual things. But then you use the invariance to bring everything back to time 0. So this dynamic has a nice invariant measure. So then if you take k to be some very large to be something very large in comparison to L. So this should not be a minus Q, this should be a Q. So K is much, much larger than some positive power of L. For some Q large but fixed, then sort of the machinery of kind of, you can see it from classical PD, but also generalizes to regularity structures. You can upper bound. So if you take your interval of time sufficiently small, then the fact that your initial condition is smaller than L tells you that over this interval of time you don't grow too much. You grow something proportionally to L. Okay, and then comes this step. So now I'm going to use some knowledge of my measure. So I'm going to say that if the supremum is smaller than so is uniformly bounded and so I have good moment bounds on the initial condition, uniformly in epsilon for all p, then I can I can just plug that into here and combine with this result and get an estimate of this type. So then I just take p to be larger than that q, and I conclude that this probability is very small as L goes to infinity uniformly in epsilon. So so this is how one would run Bourgain's argument in this setting. So what's the difficulty? And what was the difficulty for us? The difficulty for us is that moment estimates of this type, of this type. So if you just sample a gauge field according to one of these discrete Yang-Mills measures, there's no way that it's going to satisfy a moment estimate of this type. And this is because of gauge invariance. So if you think about these Yang-Mills discrete Yang-Mills models are given by they have a Gibbs factor e to the minus of an action. So their ground states are the things that minimize the action. So the discrete gauge fields that minimize the action are the ones that are flat. But flatness doesn't a priori tell you anything about the size of a one form. So it could be flat, but very kind of rough and very large, because they could be the derivatives of some. They're basically flat connections, a derivative of some gauge group element. So this knowing the fact that you have minimizers of the kind of the action that defines this mu doesn't tell you anything about their size. So this result is just not true. Okay, so what does this call for? So this essentially calls for something called gauge fixing. So we need to derive gauges or coordinate systems in which kind of applying this to our random gauge fields, we actually get good moment bounds. Okay, so how does this? So on a high level, what are we trying to do? So given a discrete gauge field U, we're going to, so here, these are the edges of the epsilon lattice. So it's a function into G, this is a gauge field. We want to find a good notion of non-flatness of U. So we want somehow a gauge invariant measure of this non-flatness of U. And we want this measure of non-flatness to satisfy two things. So if if we know that this thing is small or perhaps large, we have some information about this measure of non-flatness, then we can gauge transform U so that its Holder-Besov norm is controlled. So these Holder-Besov norms, so these C norms, in the previous slide with Bourgain's argument, I was very implicit about the actual norms here. I was assuming there was some norm for which this holds true. So the precise norms are Holder-Besov norms. This is what I'm using here. So these are Holder-Besov norms on the lattice, discrete Holder-Besov norms. So we want a bound like this, which is uniform in epsilon. And on top of this, to make this thing actually useful, we want to be able to probabilistically control these things for the Yang-Mills models that we're interested in. So we want to control moment bounds of this. So perhaps this kind of problem actually appears in geometry quite a lot. So there's a famous result of Uhlenbeck, called Uhlenbeck compactness or Uhlenbeck's regularity theorem, which essentially gives you a version of this fact, but without probability. So it gives you a candidate measure for non-flatness for this point A. So what does Uhlenbeck compactness say? So in the continuum, for a continuum one form A, you find a gauge transformation to put it into something which is called a divergence-free one form, or sometimes also called the Coulomb or Landau gauge. So Coulomb, if maybe you're a geometer, and Landau is the more common term used in physics.
So why is this? Why is it useful to put to put A into a special gauge? So you hit it with a gauge transformation to make this condition true. So why would you want to do that? Well, you know that so this A here, you should think about it as this AG. I just for compactness I relabeled them to make it A. So you know that the curvature of A is defined as dA plus A wedge A. So you can rewrite it in this form as kind of a PDE for A, and then you have this special gauge condition: d star of A is equal to 0. And now I'll use something quite special about this exterior derivative. So d plus d star is actually an elliptic operator. So d plus d star squared gives you the Laplacian on one forms, and so d plus d star squared gives you Laplacian, and so d plus d star, which is the square root, is also elliptic. And then you can use elliptic regularity to show that, okay, if at least A is sufficiently small that I can view this A squared as a perturbation of A, then I can get an estimate of this type. So I can control the Sobolev norms of A in terms of LP norms of F. Okay, so this is quite a classical observation of Uhlenbeck. And then actually you can drop the assumption that A is small, which I didn't write here, which is actually the main work in the geometric setting. Okay, so we might be tempted to try to do something like this in our setting. There's a difficulty, which is we can't really apply this kind of estimate directly because we're in a regime where we only expect some negative Holder. So we're very far from an A that we expect to have Sobolev regularity. So we're in a space where we expect only negative Holder-Besser regularity for our one forms. And this is completely analogous to how you can't actually bound Brownian motion in W1P. So even though say the H1 norm, which would play the role of the Yang-Mills energy here, is kind of the one that you'd use to define Brownian motion has infinite energy. So this is completely analogous to this. So what we instead do is we're going to define a measure of non-flatness, which is much more of a Holder type norm. Just like Brownian motion has very good properties in Holder type spaces, we're going to define a Holder type measure of non-flatness, which is given by okay, so this might look a little bit technical, in fact as technical in the name, but the idea is that you look at, so the supreme was over all rectangles in your lattice. So you have a one form on a very fine lattice, a gauge field in a very fine lattice. You look at all the rectangles inside of this lattice, and you take the holonomy of A, so the ordered product of the bonds around this rectangle, and you take its logarithm. And this gives you a Lie algebra element. And you look at the size of this Lie algebra element, and then you divide it by the size of your rectangle, so the area of the rectangle raised to the power of 1/2 minus a little bit. So you should think of this as essentially white noise scaling. So this r to the 1/2. So think of log u as being a white noise, and so you're integrating a white noise in you're integrating on a rectangle. So this is exactly the kind of behavior that you expect for white noise. And then there's this technical norm that I might comment on a little bit later. Okay, so how do we use this measure of non-flatness? So there's an idea to separate out scales. So we're going to use two different gauges, we separate out scales into something like a mesoscopic scale, so something that's kind of at small scales but not infinite. It isn't going to infinity, and then we look at something which is really at a microscopic scale. And the reason that we want to separate out two scales and use two different gauges is that this PDE that we're trying to replicate on the lattice, it's nonlinear. So you need some smallness on A in order to use the ellipticity. Otherwise, you can't view this A squared as a perturbation of this linear equation. So you need some sort of initial smallness to make this to leverage the ellipticity of the equation. So to get us to some sort of a mesoscopic scale where we can view this A squared as being something small, we're going to use something called an axial gauge. So for a gauge field U, we fix a maximal tree that the simplest thing to do is just to take edges that go around the torus. And we're given, so for this fixed U, we're given these elements U1 and U0 that are kind of the global holonomies that wind around the torus. And then it's a fact that you can gauge transform U in any way that you like to preserve these that preserves these kind of holonomies that run around the torus. These are gauge invariant observable, so you can't change them with a gauge transformation.
And so kind of geometrically, what you end up trying to do is trying to connect up the element 1, which you should think of this as like the holonomy kind of started at here, up to these holonomies that you're given as you kind of like look at these loops that wind around the torus inside the group, and you want to connect them up using paths that are kind of very close to each other, because then, for example, the difference in this Lie group between U1, U0, and U1. And the axial gauge where U is just equal to the identity on all of these horizontal bonds is going to be the difference between this final bond here between U1 and U0. So this final bond will essentially be the holonomy at that edge is going to be the difference between U0 and U1. Okay, so in the end, this ends up being kind of we end up using quite a elementary lemma from quantitative homotopy that you can actually connect all of these. So if you know that all of these points are close, you can actually find paths that are close to each other and connect one to each one of these points. And so if you apply this gauge, what you get is you get a decay in these. So you take one of these edges, you take logarithm of this gauge transform gauge field at one of these edges B, the bond B, and you multiply it by epsilon to the -1 to bring it up to a macroscopic scale, and you get a decay which is like order epsilon to the -1/2. And this is more or less equivalent to well, it should remind you that we're kind of in this kind of gauge gives you C -1/2 control on the gauge fields. And this is very suboptimal because we actually expect C0 minus control. And it's actually not enough to begin the PDE. So to begin the PDE, you need to be on the other side of that threshold with -1. So the PDE is not well posed with initial data that's in the space. Okay, but it gives us some initial smallness at least. Okay, it makes these bond variables relatively small, but not as small as we need. So to get them really to get them as small as we need, we apply a different gauge, which is this Coulomb gauge. So we're going to leverage ellipticity of a discrete PDE. So but the way that we implement this is we actually zoom in scale by scale. So as we define a gauge transformation and kind of inductively at each scale. So if it's defined, if we have a gauge transformation G that's defined at scale 2 epsilon, then we extend it to scale to scale epsilon. So like when we double when we halve the size of the lattice, in such a way that we basically end up satisfying the Coulomb gauge along the boundary of this plaquette. So we first look at like the one-dimensional subspaces of these new plaquettes. So these kind of like large circles are the elements of the larger lattice, and these dots are the elements of the smaller lattice. Satisfying this Landau gauge on each kind of hyperplane is essentially equivalent to making the gauge field along B4 equal to the gauge field along B5. So this is the most kind of regular way that you can divide the gauge field between these two bonds. And then when we move into the center of a plaquette, this is where something a little bit more interesting happens. You can find a gauge transformation to essentially make the sum of these the logarithm of the gauge field along these 4 edges roughly equal to 0. So this is roughly what this Coulomb gauge condition is doing. So this d star of log of u is equal to 0. This more or less minimizes the L2 norm of the one form that's representing u. So this is kind of a discrete analog of this Coulomb gauge. And then don't have that much time left. So what this is, I think, more or less the final thing I want to speak about. So how do we? Okay, so if we do this, then okay, why was it actually useful, and what can it do for us? So then the way that we measure regularity of one forms is by looking at their line integrals. So we have a one form on the lattice, which is log of u, and we're going to integrate it along lines. And if we can control how quickly this integral grows, we can control the size of the one form. So then, so if we look at L, which is on a fine scale at scale epsilon, then we can write out this line integral as
as the average of the line integral of A on along lines on a previous scale. So the sum is over two lines, L1 and L2, that live on previous scales, and you have so you kind of have estimates on those because you're kind of, that's what the inductive hypothesis gives you. And you should think of this term as essentially being the boundary term inside that elliptic PD. So when you have an elliptic PD, you can always control kind of, the goal is to control the interior by the boundary. So this is the boundary term. Then, so to remind you, there's the PD that we're trying to replicate is dA is equal to f of A plus A wedge A. So then, so this is the boundary contribution. Then this curvature f of A is essentially a kind of a source term, and it takes the form of being a sum over logarithms of holonomies along these in this gray area. And then there's basically Baker-Campbell-Hausdorff contributions that happen from this A wedge A. So these are kind of three terms that you need to handle in these kinds of expressions. So this boundary term, as I mentioned, you have control in it via induction. These BCH errors actually end up being relatively mild, so they're not a problem. And controlling the source term is actually the hardest part. And this is where this technical norm comes in. So the source term is not a gauge invariant quantity. It's the sum of logarithms of the holonomies of U around plaquettes. This is not a gauge invariant object. If you average the curvature, you don't get something that's gauge invariant. So this technical norm that okay, I'll just say one or two words on it. It's given by a Q variation of anti-developments of U along these rectangles, if Q variation tells you anything. And what you use it for, so the important part, you use it to control these kind of smearings, these averagings of log of UP by something which is gauge invariant, which is actually Lasso smearings. So this is so via, and here again, Young integrals appear because when you rewrite this guy in terms of that guy, you rewrite it as a Young integral or a Young sum. Actually, these are just sums. And so then the outcome is that for this special gauge, if you provided that you have some sort of initial smallness, which here takes the form that at some scale delta, these bond variables are just smaller than some constant that depends on the structure group. You can apply this gauge transformation, so this algorithm, to show that for any bond variable at smaller scales, you have a bound which is now similar to the one we saw before, but instead of epsilon to the -1/2, we have epsilon to the power of 0 minus times some constant that depends explicitly on this measure of non-flatness that we introduced. And so this is analogous to essentially C0 control. C0 minus control, and this is exactly what we wanted. So these are okay. So this is the kind of the idea that enters this these moment estimates. So actually, I just also want to say one final word on this. So there's these. So this was kind of deterministic analysis. There's also a probabilistic step, which is probabilistically controlling this measure of non-flatness. And here, this is maybe I should put this remark up top. This is the only part where we require a priori knowledge of the measure. So this probabilistic step in controlling this measure of non-flatness is the only thing we need to know, where we need to know something about these discrete Yang-Mills measures. And what we need to know about them is that they admit nice random walk representations. So we know that this holonomy of U around a rectangle is actually precisely equal in law to a random walk evaluated at the area of the rectangle times, so basically the number of plaquettes inside the rectangle, where this random walk, so this is a conditioned random walk. It's conditioned to hit a certain subgroup of your group depending on which manifold you're in. So if you're in a torus, it's the commutator group, and it has good estimates on its increments. So it has essentially Brownian-like increments. And then, so okay, so at the end of the day, we need to control these, how big this quantity, this measure of non-flatness, which contain this holonomy around rectangles, plus some Q variation of anti-development of these things. So there were there were just two ingredients that entered this, which we put into two separate appendices. So the first one is that you want to control Gaussian tails of this random walk. fact, it's not only Gaussian tails of the size of the random walk, but also its Q variation. But this is so this is possible, and we actually did this with some rough path analysis for these conditioned random walks. Well, actually for free random walks. And then actually to basically transfer the estimates for normal random walks to conditioned random walks, we need also uniform lower and upper bounds on the density of these guys, of these random walks. And this we did by essentially by Markov chain estimates on which were, so we extended some work of Hebisch-Soloff-Kost in this direction. Yeah, so this is the only part where they're working with discrete approximations of the Yang-Mills measure, but I also want to say that this is actually adaptable in some cases to non-exactly solvable models. So this we did with together with AJ last year. So we managed to control the gauge field marginal in this way for the abelian Higgs model. Okay, so let me just, okay, so actually my time is completely up. So let me just conclude with a couple of corollaries. So the first thing that you can learn about from this connection that we illustrated is that this Markov process A that we constructed in a gauge orbit, it survives for all time. So this is a kind of a cheap corollary. So this just more or less follows from ergodicity theory for SPDs. Another corollary, and this time about the actual measure, is that this gives you a very nice gauge fixed decomposition of the measure. The statement is that there exists a Gaussian free field psi and a random function, a random one form B, such that the sum of, so they're defined on the same probability space, and the sum of these is equivalent to the Yang-Mills measure. So when you project it down to gauge orbits, and this function B has good regularity properties. So it has it's almost Lipschitz. It's almost Lipschitz norm is controlled has finite moments of all orders, and this kind of proof basically follows from the decomposition of the SPD. Okay. And this generalizes the result for a previous result that I had in a paper where I also introduced this kind of similar idea of this gauge fixing procedure. And so in some sense, maybe I should have said this before, the new part in this gauge fixing procedure that we had to do was the probabilistic estimates. So we need much better probabilistic control on this measure of non-flatness. And also we need to kind of follow the analysis of this inductive gauge much better. And then, okay, so a final corollary is this kind of so we showed universality for the dynamic. You can basically project this down to universality for the measure. So basically we can show that no matter what microscopic scale you start from, whether you start from, no matter what microscopic system you start from, might be the Wilson action or the Manton action, you always converge to the same limit, which is this Yang-Mills measure. And the idea is that you can prove these moment bounds that we derive is sufficient to imply tightness of these measures, and then the universality dynamic plus uniqueness of the invariant measure really pins down the limit. There's this related work of Driver where he did a similar thing, but for R2 on the with the Wilson action. Now R2 is somehow actually easier because you don't have any topological things to consider. Well, this argument would actually work for any manifold. Okay, so just to conclude, our goal in this work was to give the first link between the Yang-Mills Langevin dynamic and the associated Euclidean QFT, and as points for what one might be interested in doing in the future. So I think the next thing to do is to understand what happens for other geometries. So for example, for the sphere, this question of uniqueness of the limit is much more subtle. So we saw this. We have uniqueness in T2, but there were very different strategies for abelian and semi-simple. And the abelian case wouldn't work on the sphere. So it's so the question here of uniqueness is much more interesting, I think. And also whether one can prove some sort of a statement for the uniqueness of this constant C in 3 dimensions. So this would require systematizing Euler estimates, as well as the fact that handling the fact that Wilson loops themselves require regularization in 3 dimensions. And then what you would really actually want to do with this is to understand what to do with non-exactly solvable models. It's like, for example, Yang-Mills Higgs or Yang-Mills in 3D. So as I mentioned, there's some work in progress on abelian 3D Yang-Mills Higgs. So I think this is there's hope of generalizing it to non-exactly solvable models. Okay, thank you very much.